So I'm Iro Limberg. I'm one of the founders of Growth Technologies. I've been working in maritime now for more than 17 years. My background is in propulsion control systems. I used to be in Rolls-Royce before studying at Croak. And at Rolls-Royce, I had various different areas of responsibility. It started off from design engineering position in control systems and electrical systems, mainly looking after frequency converters for steering gears and such. And then after that, started as head of development team for aquapilot control systems used for azimuthing thrusters. Then I moved to Norway for 5 years, where I was leading a development team for propulsion, water jet, pitch propeller, and steering gear control systems. And we developed a new system for Rolls-Royce to replace all the existing solutions that they had back then. And that solution is now in use, or has been in use for about 6 years now. And actually all the Kongsberg propulsion systems are utilizing that system nowadays if you order a new one. Then I started working a bit also on autonomous vessels back in Norway when I started work on more of a conceptual approaches, so how the maritime would be shaping out in future. And that's when we made future concepts for bridge operations called OX. And then also one of the concepts was looking at how autonomous vessels would be controlled and monitored in the future. And that was then kind of a starting point also to set up a research and development center for autonomous shipping in Turku. There I was head of R&D for that department. But then back in 2018, actually, Rolls-Royce decided to sell all of its marine business, excluding naval business, to Kongsberg. And then Kongsberg had a lot of similar solutions in place already. And it was becoming quite obvious that if I wanted to continue in my then current position, it would have required me to move back to Norway. And that's something I didn't want to do with my family. So I left Kongsberg and started out Growth Technologies with a couple of other colleagues as well. And now we've been on that journey for a bit over 2 years now. For Growth Technologies, our main investor is Mitsubishi Corporation, but we do have other investors as well. We are in that sense a bit of a different startup company that majority of our investors are actually shipping companies and ship owners. So we do have Oldendorf, which is one of the biggest bulker operator in the world. Then we have 3 Japanese tanker owners, Ueno Transtech, Asahi Tankers, and Tsurumi. And in addition to them, then the latest addition also is one Japanese investment bank, who is also our investor. So we do have quite solid background as a company. And what we are doing is that we are developing a sensor fusion based situation awareness system. I will have more on that one coming up later on. My role in the company at the moment is that I'm looking after our customer solutions and also future concepting and future R&D work and research programs. And in that side, also looking at user experience and customer experience side as well. So that's the introduction of who I am. Then let's go into the topic itself. So in this presentation, I'll be covering first different kind of sensors that I use for autonomous vessels, mainly focusing on the navigation side, not going into the health monitoring. And then after that, introducing what we are doing at Growth Technologies. So starting off, here you can see a list of different sensors that I use today, which are the kind of possible sensors to be used. And there we have first is radar and ECDIS, then the second one is LiDAR, then we have AIS, signal sensors, GNSS for positioning, IMU for motion, then camera, weather sensors, sonar, and so on. As you know, these are very similar sensors to what a self-driving car is using as well. And there you can see an illustration on what kind of functionalities self-driving car has. And this is an analog also to autonomous vessels as well, because a lot of these functionalities are very similar what a vessel needs as well. So at the moment, as you may have seen in the latest news, for example, earlier this week, Mitsubishi Shipbuilding demonstrated a solution which is close to Park Assistant. So they demonstrated autonomous berthing with a large ferry in Japan. And then there's a lot of companies already working on something that is similar to adaptive cruise control, so looking at collision avoidance capable navigation systems. And then the other ones as well. So traffic sign recognition for us, what it means is basically situation awareness system looking at what's happening around us and what kind of limitations we have, and so on. So the analog in that sense is quite similar as well. And the sensors used in some cases are similar also to car industry. So you can see by different colors, you can see what kind of sensors are today used for cars in different use cases. Of course, the main difference here is that the adaptability for cars, you have to act much faster than for vessels. For the vessels, the decision-making time is really long. Then I will go through these situational awareness sensors in more detail, each one by one. So let's start off with radar. Of course, radar, as you know, is the main source of surrounding information for crew today. It detects vessel and other objects, including non-AIS targets, and shows the reflection of those. And you can determine the size from reflection, but also the reflection can show you shades, so it can be a bit misleading as well. Configuration-wise, there are multiple options for configuring your radar. You can set it to different area, and there are tracking functionalities and such. When you're new to vessels, it might be in some cases challenging to adopt the delay of radars compared to real world, because there are certain delays. Of course, that depends also on the manufacturer and model, but the delays, what you're seeing on radar screen to real life can be up to 20 seconds or 30 seconds in some cases as well. And also one of the pain points of using radar is that there is no terrain information usually, and the markings on the map make it difficult for crew to understand their positional relationships. Of course, over time you will get better on understanding the terrain in radar and so on, but this is the pain point we have been highlighting. Second sensor introduced is ECDIS, mainly used today for route planning and map information. When going towards autonomous shipping, ECDIS is in that sense very critical component, because it's critical for e-navigation and information sharing as well, because all vessels more or less have ECDIS already. So that's kind of the existing infrastructure that is already in place. ECDIS can utilize also sensor fusion. So it can have overlays for AIS data and also for radar data, and to some extent also LiDAR if the functionality exists. And this of course depends on the age of the system more or less, if they have LiDAR integration or not. What are then the pain points of ECDIS system? It's that it has many unused features and unknown icons, which are causing the crew to miss out on potential beneficial features. So when ECDIS was introduced, it had a lot of functionalities already then, and over the times there's been introduction of a lot of new features. But the challenge is that not that many on board are familiar with all the possible functionalities and how you can use ECDIS system. This causes the end result that the users are using only the small portion of the system that they are familiar with. So that's challenge there. And this illustration just shows this kind of e-navigation infrastructure. So how you can share data and have connection to different vessels and different sources. And there's been recently a lot of activity, especially on just-in-time arrival. projects which have been utilizing ECDIS as the information sharing system, so providing accurate arrival times to ports. And then also on the just at least on the European Union's just-in-time arrival program, they were also looking at this kind of route exchange. So you would exchange your route information with the closest vessels to you, so that everyone would be aware what's happening around us and what kind of decisions are being made. Then LiDAR, a very interesting sensor, quite new in maritime. Basically what LiDAR does, it's scanning the environment by sending out laser beams, and based on the reflection back, it will create a 3D model on the surroundings. Very useful. The challenge is that it's quite expensive, and the range is also an issue. So at the moment, LiDAR that can scan up to 800 meters costs about more than $50,000 US. I think it was about 75,000 at the moment. So as such, it's really expensive comparing the range that you can see. But then on the automotive side, for example, Velodyne has been developing a new low-cost LiDAR for some time already, and the target cost there is $99 US per unit. And the cost comes here from scale of economics, so that when you can have cheap sensor that you can put into many use cases, then you can get the price down as well. Recently, there has been actually LiDARs were mainly manufactured in Canada for some time. But what we've seen during the last year or so is that in China, there's a lot of new companies coming up, which basically means that the cost of LiDARs will be coming drastically down as well. But then the challenge is still the range. So for docking assistance systems, 100 meters is sufficient, and you can have, if it's $99, you can have, for example, 10 sensors around your vessel, and you can create very comprehensive 3D model of the surroundings utilizing those. But for navigation decisions and longer term and longer voyages, then it's not that useful, because basically in open seas, LiDAR doesn't see anything; it's just pitch black. Yeah, so the cost is an issue if you compare it to the range what you're seeing, and then we can use tens of LiDARs around the vessel to create one 3D map. So how LiDARs work is that you can connect them, all of those together, and then just create one 3D illustration out of the sensors. So you don't have to take each sensor as an individual one, but you can make a multiple ones. Also, you can utilize LiDARs for positioning information, especially in rivers and areas where you have reflections back. So for example, you can see it from the illustration here, which is taken in Turku. So you can see quite well the location and the building and everything else. So with this one, you can quite easily map it to the actual environment and how it looks. And then through your GPS positioning from there, or location positioning. Best use cases are in narrow channels and port areas. And as mentioned, there is not that much use for LiDARs in open seas. One of the benefits also for LiDARs is that you can use it also to scan ice. So with LiDAR will detect ice, and you can also detect the ice thickness and ice formations as well. So I assume that in future we will be seeing quite many applications where ice navigation is utilizing LiDARs as well. And this is really interesting going forward also for autonomous vessels as a sensor. And then also one of the benefits for utilizing LiDAR is that once you've used it on, if you have, for example, a ferry that is going between a certain route, the scanned 3D world will exist on your next journey as well. So once you've scanned the area already once, then you have the main 3D model created. And what happens is that the LiDAR will only update the current model. So in that sense, you will also see your previous track and where you've been before, and then because it will see also the air bubbles coming from your wake. So that in that sense, you're also creating your route information to the 3D world. And when you're coming back, then it's been updated. So the 3D map is kind of the most powerful thing when utilizing lidars and what you're creating, and there's a lot of things you can do there. And you can also use it for replication of real world in challenging weather conditions. So for example, if you have very dense fog, just consider a situation now like in this picture in Turku, the 3D picture. If it would be foggy conditions outside and you'd still see this kind of 3D illustration of your surroundings, then it's really easy to navigate in that sense, at least the main items. So you will see what things are and where they are. So it makes it kind of a digital twin type of approach as well. Pain points, as mentioned quite many times already, are the range, environmental conditions, and cost. So for the environmental conditions, I mean that when it's raining, then the lidar is sending out the beams, but they can be reflecting back from water droplets, which means that the distance is becoming shorter. Then AIS sensors, I think you're all familiar with these. One of the challenges with AI is that it's not fully reliable at all. And some vessels have it on, some turn it off. Especially in the Middle East, it's quite common to turn it off for larger tankers when they're going into countries which are not so favored in global aspects. And then we've seen a lot of misinformation in AIS. So vessels which are, for example, tankers, change their AIS vessel definition to fishing boats, and vice versa as well. In fishing, it's not mandatory to use it, but those who use it may turn it off so that no one knows where they are fishing. There are two types of AIS solutions. There's the terrestrial, which is utilizing the antennas, satellite antennas on shoreside. And then there's the satellite system, which is utilizing satellites. And the satellite system has a slightly longer delay, and it may be expensive to use as well. The good thing about AIS is that it's kind of an established infrastructure to share information between vessels as well, in addition to the location information. I will have one example on why autonomous vessels cannot use AIS signal as source coming up in the slides. Then IMU. IMU is used to define the vessel's own movements. So it's looking at the yaw and roll and pitch of the vessel. And this is, for example, needed to stabilize camera images and augmentation if you're showing, for example, video feed from vessel, so that it's not rocking and rolling in the same manner. Then for positioning GNSS, so there is a global GNSS satellite infrastructure in place. So all the major areas have their own signals. Mostly used is GPS satellites at the moment. Then Europe has its own Galileo installation, which is only non-military use and not single control, nation controlled, because the other ones are military controlled. So, for example, if there would be a scenario where if a war breaks out, that would mean that all GPS signals are switched off, most likely. So that would mean that there wouldn't be any system that utilizes GPS that would work after that. And same applies for the other ones. And that's one of the reasons also why they have their own satellites, is that they can utilize themselves those, but block everyone else from using. And these are highly military controlled in that sense. So Russia has GLONASS, China has Beidou, Japan has something called QZSS, and India has NAVIC. But if you're using global GNSS as a receiver, then you're receiving the signal from all of these satellites, and you're utilizing all of them in that sense. There are some known errors in all of these, and of course, one of the challenges is always this kind of spoofing and jamming. So basically how that happens is that, for example, if you want to spoof the location of where the GPS is showing, it's fairly easy. because the GPS, for example, the receivers are always listening to the strongest signal. So if you take your rowing boat and go next to, for example, a Viking Grace, and then put in your own GPS sender and set the location there, then it will be the sensors on board the vessel will think that you are the actual position that they're receiving, and then you can spoof it that way. Of course, there are ways to detect this kind of spoofing, and quite many vessels are using this kind of spoofing detection systems. It's comparing multiple sources and the signal strengths as well. Then one quite common error also is jamming. This is especially what we've seen in Finland quite a lot, based from or coming from Russia. So that means that the GPS signals are jammed so that you don't get any or GPS or location information from the satellites, or you get false information, which goes under spoofing. Then there's 3 examples of errors that has happened for GLONASS back in 2014. There was an upload error that meant that the constellation was sending position errors. So it was sending all the GLONASS signals were 50 kilometers off in the wrong position. And this meant that they had to take the system down and reload it again, and meant that it was off air for 11 hours. Then for GPS 2014, there's a clock error in satellite, which resulted in position errors. And in 2016, there was a timing error that affected the accuracy of the signals as well. Then for the European Galileo system back in July 2019, there was a problem with the precise timing facility that caused the system to be off air for several days when they started to fix that. And then in December 2020, the system was off air for 6 hours due to time determination problem. So these are not by any means bulletproof systems and always reliable. So there are errors also in these satellite systems, which need to be taken into account as well if you're looking at autonomous vessels and navigation position information. Then there's also this kind of regional network that is ground and satellite, working with ground and satellite systems that boost the accuracy and provide better location information. And you can use this kind of so-called RTK systems, which are then also providing more accurate and timely position information and more reliable one as well. And then on the right hand side, you can just see a map where there's these different areas for these S-bus service areas and where they operate. Then, like I've mentioned a couple of times before, one positioning system is not enough for an autonomous vessel, just because they're so, in the end, they're unreliable. So you need multiple sources to define your own position. You can have the global ones, so like GNSS type. Then there are also regional positioning informations coming from ELORAN, for example. Then you can use the local ones from VDES or radar. And then there's other kind of integrated services that can be utilized, and from where you can define your position, for example, looking at the depth around you and make the location based on that. And for this, I think the next big thing will be these new S100 maps, which will be providing also the depth information. So once you have those maps in place, then utilizing sonars, it should be fairly straightforward to define your position based on seabed as well. Of course, this doesn't apply to deep sea, but in coastal areas at least. And then, of course, you can do a lot of clever things with IMUs, looking at your own movement based on your own speed and heading. And then also you can build the location based on LiDAR in coastal areas as well. So then camera as a sensor. You can see also a video feed from one ferry operating in the archipelago in Turku, where we have our camera system for development use as well. So for autonomous vessels, cameras are used to replace the human eyes and binoculars. They can be used to provide feed for remote control. And in that case, it might be usable to have 360-degree view through a virtual setup. So in principle, from my proposals, how I would set up a remote control center is that normally you're getting this kind of a virtual representation of what's happening around you. And in case of intervention, then you can take, for example, VR glasses or something like that, and then have a live video feed from your vessel only then. So this way you're not utilizing that much bandwidth, and you only use video feed when you actually need that. The video feeds and the cameras can be with or without machine vision based object detection and distance estimations. So on the video on the right hand side, you can see, for example, how the distance works. So there's an object, and to that object we have algorithm based distance calculations all the time active. So we know how far these objects are. And then the object detection itself can be seen on the left-hand side, where you can see these kind of boundary boxes around the objects that we have detected and further information for each object. From camera side, there are different kind of options, what type of camera you utilize. Most common ones are day camera and a thermal camera for night vision. And the accuracy of object detection is always based on pixels, because the machine vision is doing object detection classification based on pixels. So it's looking at which pixels are changing and then looking from those pixels, the model database, which pixel formations look similar, and then judging the classification based on that information. And now you can see here from the videos how far away the vessels are from us, and when the ferry is slowing down, you can see the distances to those. And this may be to some of you also a familiar place in the archipelago. Then, as a summary from different sensors, there are many different sensors as explained here. They all have different purposes. They kind of all complement each other in that sense. But the sensor fusion is the key here. So utilizing different sensors are fusing the information together, which then means that when you're fusing the information, you're taking the best bits out of each of the sensor and not just looking at one source of data. And here's an example of normal life sensor fusion. So in car navigators and navigation systems, there is behind that system, there's a fusion of map, traffic signs, location, and your own speed. And all of these information fused together will provide you the information you're seeing, for example, in Google Maps when you're utilizing it for your navigation purposes in cars. So we need multiple sources for same information in order to filter out the fault tolerances. And then this presentation here only covers small portions. So there's a lot of different kind of sensors, especially on the military side. But the main thing for commercial maritime is then also the cost aspect as well. So instead of just utilizing all possible sensors, one needs to evaluate what is making sense and where the cost is in regards to the use case. Then here's one recent example I came across in LinkedIn. This is from Furuno's situational awareness system. They are mainly utilizing radar information and AIS data, but they are not doing sensor fusion. So they are not matching those together. They are only providing both of them as individual information. And here you can see that how much deviation you have in AIS signals, for example. You can see on the lower left-hand corner, you can see the both tugboats around the vessel. and then you can see where their AIS signals are in correlation. So the red vessels are AIS signal vessels, and then you can see it in the live video feed where they actually are. And same thing on the upper left hand as well. So you can see that there's some deviation, but if this would be an autonomous vessel, then this deviation would be quite catastrophic in many senses, because you would be avoiding vessels that are not actually there where you think they are, and so on. And on the larger picture on the right-hand side, you can also see how important it is that the heading of the other vessels is taken into account. And I think there's a misinformation coming from the bulker in the key side. So that's stationary, but the AIS signal is, I think, wobbling a bit. So therefore it's turning around, which causes its bow to be on top of us. And if this would be fully autonomous vessel, this where we have these sensors on board and showing the video feed from, then it would be quite catastrophic avoidance situation. Because on the left-hand side, we can see the small boats, and then we would have this one red boat, which we would be avoiding. So we would be actually colliding with the small boats because we would be making evasive actions that are not based on any proper information. So this is just an indication on why you have to do sensor fusion and why you have to compile information from different sources. If in this case they would utilize also machine vision in this solution, they would be able to say that, okay, our machine vision system is placing the bulker on different heading, and then we can match that AIS signal to that instead of showing this kind of non-filtered information. So that's a generic part. Just checking what time it is, how much I have left. So then the next bit is what is Croak and what we are doing. So going through that in a bit more detail. So this was the starting point for Croak Technology and why we started our company. There are 6 main reasons for collisions to happen at sea. The first one is bad decision making, second one poor lookout, then inefficient use of radar, inexperience, lack of communication, and I would say that now the last point after COVID, the last point has become even more important, is fatigue. When we are seeing that the crew change times have become longer, and the crew on board are spending more and more time on board. And unfortunately, we are seeing also quite a lot of mental issues within the crew members as well, which are then put under fatigue. And this is seen then in different kind of behaviors, like, for example, drinking alcohol on board. And we have seen quite unfortunate cases recently related to this kind of incidents. But then, how is our system addressing these challenges? So we have carried out quite a lot of user interviews and collected comments from users. What are the challenges they face today? And one ex-captain said that it's very difficult at night time to mix up ships, especially when talking with other crew members, because during daytime you can refer them with colors, for example, the red ship or on the port side and so on. But at night everything is blank, so it's really difficult. But with our system, we have something called image blending, where we can bring in more details about each vessel also during nighttime. So we can provide distinctive features from vessels in that sense. Then one feedback from a young crew member was that what AIS and radar show, it doesn't match one-to-one with what they're seeing outside. So especially for younger crew members, they have harder time telling which ship is actually which on, for example, radar screen. In our system, we don't have delays. So what we are showing the same things that you're seeing in the real world in our augmented reality view as well. So we don't have this kind of similar delays that make it challenging. Then for tracking, there are some issues that are related to how you can track 3 different vessels. For example, if you have multiple vessels, in our solution, you can select which vessels to track or track all of them. I think it was currently you can track 30 vessels at same time. So you can select the vessels you want to track, and the system will handle the rest. Then there was also feedback about the delays, and as mentioned already before, our system is working on real time and not with delays. Then there's lack of detail. So sometimes because of the radar lack, it's hard to keep track on faster vessels. And this is where our machine vision comes in. So the machine vision is also tracking fast motorboats and all other vessels as well, and boats as well. And with the prediction algorithms that we are utilizing, we are also looking at the direction where they are heading and providing that information to users. And then for the ship sizes, those are sometimes hard to determine from radar image. In our system, we have different classifications that our machine vision is utilizing. We are taking these classifications directly from AIS system, so we can also match our machine vision detection to AIS as well. And there you can see the different categories we are using for vessels. And then for in addition to the vessel type, we are also providing information if it's small, medium, or large size as well. I talked already previously about the sensor fusion. So here is just the example of the sensor fusion, and our system centralizes all of these inputs and then does the sensor fusion on board. And what it basically means and how it works is that we have multiple data sources. All of those data sources are taken into the system, and then our CPU magically puts all of the information together and provides it as an output to our user interface. So it's taking the best bits of all of these different sources, filtering out the bad parts, so to say, and then we can show it in the UI, or either on board, or we can also through our cloud solutions send the information to shoreside as well. What is included in our scope of delivery is that we have our own camera system that we have developed, and the camera includes two different cameras. So there's normal camera with 225 degrees field of view. So this is fulfilling the SOLAS watchkeeping requirement as such with one camera. And then we also have 180-degree thermal camera as well. Then we have the central unit where all of our processing power is. So there's NVIDIA GPUs included there. Then we have a couple of different options for displays. So we always deliver our tablet-based display, but then there's also option for fixed screens. So you can have either roof display or normal monitor in your consoles. And this is just to illustrate how large the field of view is when it's 225 degrees. And this is the same requirement that is set out in SOLAS for watchkeeping. So everyone who's on board should have this kind of visibility when they're looking out. But as you all may be aware that it's not that simple that from one steering position you would be able to see 225 around your vessel. So quite often you just have limited 180 view from the bridge, and then you have to go out to the wings to see more. And then that's also why for our type of system, it's quite critical where the cameras are positioned so that it's unobstructed view from the location. And then in our system, we can track and identify ships and predict their movements. Also, the vessels without AIS signal, either if they have switched it off or if they don't have it, we can still detect those and inform the user about where they are. And because the field of view is 225 degrees, we have a panning option, so the user can select a certain field of view they want to be focused on instead of looking at the whole 225 if they want. Of course, they can look at the whole view, but it's usually too much information. Then also one of the unique things that we have that the others don't have is something called image blending. basically what it means that we are putting on top of each other both image feeds, so the thermal feed and the normal camera feed. And this goes back to the same principle of sensor fusion that I mentioned earlier. So from a normal day camera view, we are taking out the colors, for example, navigation lights and such. And then from the thermal view, we are taking the thermal information. This means that in nighttime conditions, for example, we will see the thermal imaging of the night with colors, which is unique. And this is how the main benefit of thermal blending. And then the user can themselves select how much blending they want to have between the thermal image and the day camera image. Then looking at a bit about our evolution, so where we are today and where we're heading. So at the moment we are developing and providing awareness system. Currently it's been piloted on 2 vessels, one in Japan and one here in Europe. And then we have 7 vessels which are collecting data for us for the machine vision teaching. Situational awareness system is kind of the foundational building block for autonomy. So whatever the solution is, you will always need a situational awareness system. So that's why we've also started from this system. The next one, what we will focusing on is navigation assistance solution. That basically is a solution that is then looking more on the navigation side, so providing crew information on collision avoidance situations, route plannings, and such. And then in future, these solutions are leading towards autonomous vessels, and the offering is also towards that. And here's just one latest illustration from our pilot. So there you can see our camera in action on Polaris. So Polaris is running normally between Rauma and Rostock. At the moment, it's actually going to, I think it was going to Bilbao, Santander. So it's in Spain at the moment. And as you can see, as a startup, we don't have always the best facility. So there you can see one of our engineers doing some adjustment works in the port of Rauma in a bit wintry conditions. So this was about a week or 2 weeks ago, and we did some adjustments on the vessel. And then you can see the UI, which is currently being used on board as well. So they have a Samsung tablet from where they can access and see the system, how it behaves and what's happening around them. And in this illustration, you can see the AIS detection vessels, and then you can see a satellite map also of the surroundings. All right, that's brief package about sensors and how to utilize sensors for autonomous vessels. If there's any questions, I'm glad to answer.